Lesson 14.2, Task 3. Graph geometric sequences. You can graph a geometric sequence given the explicit rule for the sequence. So we're going to graph the sequence f of n equals 20 times 1.5 raised to the n minus 1 power for all n between 1 and 5. Use the explicit rule to make a table of values, then plot the points. All right, so we use n 1 through 5, that's our domain, and then we're going to use f of n, this would be our range, this would be our y value, this would be x and y if we were using x and y, but we're using n and f of n. And when you plug in 0, or plug in 1 minus 1 is 0, anything to the 0 power is 1, times 20 is 20, and each one of these you plug in 2, you're going to get this answer here. So this is our domain, this is our range. So to graph that, you put the domain on the x-axis, here's our n's, and we put the range on our y-axis, which is in this case f of n. All right, so you can see the scale goes by ones on the bottom, and it goes by tens up the vertical side. Okay, so if you graph these points, it would look like these dots here. You're not going to connect the dots because this is just individual points. Okay, so with the sequence, it's just those points. It's not a connected line. All right, so it says, how is the data in the table used to graph the sequence? Each column of data shows the data pairs n and f of n that are plotted on the graph, where n is the horizontal distance from the origin and f of n is the vertical distance. All right, so that is true. N is your horizontal, f of n is your vertical. Okay? So this one it switches, but n is not the vertical. So the first one has to be correct. Which statements are true? Select all that apply. The domain, all right, we looked at the domain. The domain would be our n's, so 1 through 5. And the range would be the f of n, so 20, 30, up through 101.25. So this would be our range. And that would be how you find the domain and range from a geometric sequence. All right, that's all for task 3. If you have any questions, let me know. Lesson 14.2, task 4. Graph geometric sequences. You can also write an explicit rule for a geometric sequence given its graph. Part of a geometric sequence is shown on the graph. Write an explicit rule for the sequence. All right, so first thing, let's go ahead and make a table that will help us see what we have. So we've got n, and we've got f of n. And if we make a table, we're going to see that it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we've got 12, 15, 405, 135. Let's see, I'm going to have to make this a little bit better. Let's write these down instead of sideways. All right, n, f of n. This way I'll have more room. So 1, 2, 3, 4, 5, 6. So 1 goes with 12, 15, 405, 135, 45, 15, and 6 goes with 5. All right, now it just makes it a little easier to see the ordered pairs from the graph. All right, the first one says complete the statements describing how to find f of 1. So this is your first term using the graph. Locate the ordered pair with n equals 1. So here's n equals 1. We can see that goes with 12, 15. So the second coordinate of the ordered pair, f of n, so your f of n is 12, 15. And you can see that straight from the graph here, but it's easy to see if you make a table as well. All right, so it says find the common ratio. So remember, to find the common ratio, we've got to say what multiplies to get to the next term. So basically you can divide each one by the previous term. So if we do 405 divided by 1215, that equals 1/3. And if I do each one of these (5 divided by 15 is 1/3, 15 divided by 45 is 1/3. Each one of those is equal to 1/3. So our common ratio is 1/3. So to write an explicit rule, we go back to the formula that we were given. So our formula was f of n, and it was our first term times the common ratio to n minus 1. This was a formula you were supposed to write down. So our first term here is 1215 times r, which is 1/3 we just found, to the n minus 1 power. So that would be how we find the nth term of this sequence. So that is your explicit rule. That's your explicit formula. They call it a rule, but it's the same thing as a formula. And that works for finding any term in this sequence. All right, it says, which statement best describes how the graph can be used to reason why the common ratio r is greater than 0 but less than 1. So 1/3 represents exponential decay. So if we look at the graph, you can see that this is an exponential decay function. It's decreasing. So as the n's get larger, the f of n's get smaller, which would be exponential decay. All right, so it says the graph shows a decreasing function multiplying by a common ratio greater than 0 but less than 1 will result in lesser output values for each successive input values. All right, so each output was less. The graph shows that the first coordinate of each ordered pair is less. That's not true because the first part of each ordered pair goes up by 1 each time. All right, so that's all for task 4. If you have any questions, let me know. Lesson 14.2, Task 5. Convert between forms of geometric sequences. Every geometric sequence can be written both recursively and explicitly. Your general recursive rule with common ratio r is your first term, okay? F of 1 equals your first term, has to be stated, and then f of n equals your common ratio r times f times n minus 1, so your previous term. In your general explicit rule with a common ratio r is f of n equals your first term times your ratio raised to the n minus 1 power. So these are both things that we've looked at, and now you're going to look at converting from one to the other. All right, so it says a sequence of A notes can be played on an 88-key piano as shown in the table. All right, so an A note, so 0 through 7, and then here are the frequencies for these A notes. All right, so it says a frequency doubles from one A note to the next higher A note. From lowest to highest, the frequencies of A notes can be modeled by the recursive rule. So you can see that this times 2 is this times 2 is this times 2 is this. Or if you take this, divide it by this, you get 2. So our common ratio is 2. All right, so it says f of 0 equals 27.5. That's straight from the table here. 0 equals 27.5. And then it says f of n equals twice, so 2 times f of n minus 1. That's for all n between 1 to 7, where n is an integer. All right, so now it says convert this recursive rule to an explicit rule. All right, so it says write an explicit rule for the sequence. So your first term of the sequence is f of 0 equals 27.5. And the common ratio r is 2. So an explicit rule for this sequence would be 27.5 times 2 raised to the n power. And this would be for all n from 0 to 7. So you can see that these are a little bit different. So for the recursive rule, they're going from 1 to 7, and the explicit rule is using all of them from 0 to 7. Okay? All right, so it says, how can you use the table to find the value of n for which this equation equals 440? So if you come up here, 440 goes with 4. So A note number 4. So the rule would be 27.5 times 2 to the 4th power equals 440. Because remember, the common ratio again was 2, and then n is the power. All right, it says, which statement about the domain of the explicit rule and recursive rule are true? Select all that apply. All right, so if you remember before, there was a little bit difference. There's a little difference here. So in the recursive rule, it goes from 1 to 7, and the explicit rule goes from 0 to 7. So just a little bit of a difference there. So we can say that the recursive rule, okay, here's recursive. The domain of the recursive rule goes from 1 to 7, and the domain of the explicit rule goes from 0 to 7. All right, so that means the explicit rule and recursive rules have different domains. All right, so they do have a different domain. All right, so that is all for task 5. If you have any questions, please let me know.